Okay, the build versus buy decision. It's a specialized skill. Years of design expertise go into building a reliable and effective power supply. Switching mode architectures are a lot more complicated than a simple linear design. Also, semiconductor process technology innovations such as silicon carbide and gallium nitride responsible for driving switch mode architectural. Yeah, so here the principle is the same. In the case of an AC-DC power supply, there are a couple of stages, including rectification of a single-phase 230 volt AC or three-phase 400 volt AC 50 Hz mains voltage before the DC-DC conversion stages. In both cases, in a DC-DC conversion stage, a primary circuit of power semiconductors, a power switch circuit, generates a high frequency alternating voltage to a transformer. This causes a current in the primary windings that will induce an alternating current in the secondary windings. So a secondary voltage is built up. The winding ratio of the transformer specifies stepping up a voltage. The winding ratio of the transformer specifies stepping up or down. A secondary circuit rectifies the high frequency voltage and could create a feedback signal to the primary electronics for regulation. So here we have a buck step down switching converter, and here's a simplified boost converter. Here is the architecture of a typical switch mode power supply. So you have the AC in, so the socket in the wall. It goes into a filter, then a rectifier, an active PFC, or whatever that is. So voltage, current, okay. And then a switching element where you have a PWM driver to the transformer, rectifier again. There's a reference air amplifier, which I guess is used to then modify or error correct the input to have a better or correct output, maybe. Input filter serves to remove any damaging voltage transient and surges on the mains input from entering and causing damage when in the power supply. Okay. Right, where's the middle again now? So, just to draw it up again, I always like doing this, at least that I kind of learn how it's done. I get more versed in what is actually going on. Because you can build something, but you can also build something and still not understand how it works. That's a problem. Or at least it will be. So we have, so this is the AC. And then you have an input filter. So EMI filter, I would assume. I make that red. And then what happens afterwards? So the filter filters out, or how to say, serves to remove any damaging voltage transients and surges on the mains input from entering and causing damage within the power supply. The filter also aids removal of any electromagnetic interference generated within the switching circuit from being conducted out to the AC mains. So it also works in the opposite direction then. Switching circuit typically operates from 25 kHz up to 500 kHz and is a source of EMI. Noise entering from the mains has two components, common mode and differential mode noise. Common mode relates to noise measured between either live or neutral or earth. Differential noise is between live and neutral. Combination of inductors, chokes, capacitors form a filter arrangement to attenuate both types of noise. So it could be like a common mode choke, filters noise in both directions. Is that alright to say? Filters noise in both directions. So you have input common mode noise and differential mode noise. So you might have a choke first, and then you might have a EMI filter, a pi filter, capacitor, farad bead or something, and another capacitor. Just try to make it as simple as possible. Like I said, we're learning here. Rectification. The filtered AC input voltage passes through a bridge rectifier arrangement to create a pulsating DC voltage. A smoothing bulk capacitor removes line ripple from the rectified voltage and provide a voltage hold-up function. The filtered AC, so after the filter, it's the filtered AC. You can also just put that on here. Filtered AC. So it's effectively the same, I think. Rectification. That sounds like a green thing. I'll put this in there. AC, filtered AC. Just to kind of understand that it's the same, but it's just filtered. So you kind of look like, if you think about a lot of noise, how does a noisy AC signal look like? Noisy AC signal. fun to just search it. This is an AC signal with random noise. So you have the positive pulse, negative pulse, and as you can see, it's like ripples all over. Signal plus noise, here's a noise. So it doesn't look good, basically. Then you add this filter, or these filters, different types of methods, which we will get into and learn. And then you have a filtered AC, which then would look, maybe it would look nicer, so cleaner. And then you go through rectification. It takes the alternating current and it strips away the negative one, negative pulse. Passes through a bridge rectifier arrangement to create a pulse-aiding DC voltage. Just searching up, like, to understand like what that means. So here you have a sinusoidal signal, so AC signal. And then after rectification, you would get something like this. Halfway, if you use a halfway rectifier, because you take, yeah. So here's the signal. And if you're thinking back of this diode that was here somewhere, this diode, and if you only have one diode or two diodes or something, some type of configuration, you'll only strip away. So if this is a halfway rectification, it will conduct, current will pass through the diode in the positive pulse, while in the negative one it will not conduct. So you basically lose that part of the signal. And then it will continue again. Positive, negative, nothing. Positive, nothing. But with the full wave rectification, this 4-diode bridge rectifier, as I read before, you convert that negative pulse and you use it again somehow. And I remember this from my study time with full bridge rectifiers or rectification in more simple terms. But okay, going back to pulse DC is a periodic current which changes in value but never changes direction. Consisting of one or more rectangular flap top rather than sinusoidal pulses. So pulse DC is from a halfway rectifier or full wave rectifier. So that's a pulsed DC then. This is a pulsed DC, or this one. Yeah, here we have direct current, pulsating and alternating. So it has a bit of the same properties. Or same characteristics of both alternating current and direct current. Okay. So can we say, I'm being bold here, can we say that this is then a pulse DC? but it's not. Yeah, it is, basically. So you have the filtered, which is still in sinusoidal signal. Then you go through the rectification and you take away the negative portion of the signal. But it's still effectively sort of behaving like an AC signal. It's pulsating. Huh. Okay. Just write wall socket. I'll make these a bit smaller. Oh, 36. 36. Strips away the negative portion. Just give myself a few sentences or something to kind of look back on. Okay, so after rectifier, what happens? Power factor correction. This is an essential aspect of any power supply design larger than 75 watt and on LED PSUs larger than 20 watts, and relates to the difference between the real power used and the actual apparent current taken, expressed as a ratio. This is the power factor. In ideal circumstances, this ratio should be unity, 1. However, the charge current behavior of the bulk capacitor used in the rectification stage distorts the sinusoidal AC mains waveform. Passive power factor correction techniques typically use an inductor in the live input to reduce the peaks of the sine wave, reducing potential harmonic distortion and improving the power factor. However, this can reduce efficiency. Today, most AC/DC switch power supplies employ active power factor correction techniques. Often a boost converter circuit is used to control the shape of the waveform. I don't get this. What am I supposed to do with this? Power factor. And relates to the difference between the real power used and the actual apparent current taken, expressed as a ratio. Difference between real power used and actual apparent current taken. Okay. What is the FC in switch mode power supplies? Circuit improves the efficiency of power consumption by ensuring the input current is in phase with the input voltage. So that's what we see here. We see phase shift. So what this power factor corrector does, and it's an active one, it improves efficiency by ensuring the input current is in phase with input voltage, similar to a pure resistive load, by correcting the current's shape to be sinusoidal and in phase with the voltage. It reduces energy waste, decreases energy costs, minimizing electromagnetic interference, and helps electronic devices comply with power quality regulations like the IEC 61032 standard. Okay, so we go from a pulse DC to a active power factor corrector. Correction. Make this a bit darker green, maybe? No. Ensures input current is in phase with input voltage. More of the drawn power is converted into useful work. Less wasted energy means lower electricity bills. So what it is it's efficiency. Reduces energy waste. It improves the efficiency of power consumption by ensuring the input current is in phase with the input voltage, similar to a pure resistive load. With no energy being stored or returned to the circuit. The most defining characteristic is the zero phase difference between the voltage and the current waveforms. Electrical energy is completely converted into other forms of energy, primarily heat. So there's no energy storage, power factor 1. Okay, so the power factor is 1 then. Or you want it to be, at least. So this is what that does, is ensures the input current is in phase with input voltage in order to have a power factor of 1. In ideal circumstances, this ratio should be unity. However, the charge current behavior of the bulk capacitor used in the rectification state distorts the sinusoidal AC mains waveform. So it's not ideal in that sense, because it has energy storage. So it can't really be in phase with each other. It's basically like this takes me back a little bit to reading about impedance matching. When you have reactance and stuff. I'm not gonna pretend like I remember everything, but looking at impedance matching and checking what impedance you have of a signal. See, you are measuring return loss or something. You can basically see where there is reactance or the non-resistive component of impedance in an AC circuit arising from the effect of inductance or capacitance, or both, and causing the current to be out of phase with the electromotive force causing it. Damn. How cool is that? So, reactance is the non-resistive component of impedance in an AC circuit arising from the effect of inductance or capacitance, or both, causing the current to be out of phase with the electromotive force causing it. I'll take a wild guess that in order for us to ensure input current is in phase with the input voltage would be to somehow impedance match. But I don't know. I don't know how you solve it. How do you ensure? Oh, that is cool. That is cool. I'm glad I'm getting into this. And that is basically what is said here too. So that's cool. Let's see. However, the charge current behavior of the bulk capacitor used in the rectification stage distorts the sinusoidal AC mains waveform. So ideally, you have a resistive load where the input current is equal to the input voltage, or is in phase with each other. But if you have reactance, they will be out of phase with each other. So how do you compensate? Okay. So I'm not sure what this is. Like, put some question marks around it because it's here. At least I know, some rectification, some diodes, bridge rectifier has to be, here's filters, chokes. What is here? More capacitance, more inductance, more filters somehow. Not sure. Proactive power techniques. Often a boost converter circuit is used to control the shape of the waveform, improving the power factor and limit the harmonic distortion. Passive power factor correction techniques typically use an inductor in the live input to reduce the peaks of the sine wave. So this improves the power factor, but it reduces efficiency. Okay, let's jump on so we don't get, so we're not stuck in one thing. But we're on the switching element. So switching function, compromising the switching power semiconductors, the transformer and the driver IC. Together they created a high alternating voltage for the transformer. The turns ratio of the transformer permits a step up or step down of voltage, as well as serving to provide an isolation barrier. Switching frequencies can vary from 25 kHz up to 500 kHz or more. The frequency and/or the duty cycle of the PWM signal can vary depending on the load imposed on the output. During the design of the switching function, adhere to EMI best practice is essential to minimize the conducted and radiated emission to meet regulatory standards. Yes, and this is important. This is a very, very important topic when it comes to switching power supplies, which is probably the most exciting things, and where you can really make problems for yourself. I will write a bit in phased DC or in phase post DC. So we want to have them in like a unity stage where the input current is in phase with the input voltage. So we use techniques, actives or active or passive techniques in order to solve that, and then we get more of an in-phase pulse DC. And then we go to the switching. So here we get then a signal going in. No, wait, we need a driver. We need a driver. So I'm gonna do like this, flip that. PWM driver. Right. So switch. I would just write switch, and then it will go out again. I'll wait with that. So compromising the switching power semiconductors. Comprising. Tap into the music. So here, power factor correct. Okay, so here is an active example of AC power conversion. You have EMI filter and bridge rectifier, and then you have a boost converter. So here's an active one. We use a boost converter in order to get 400 volt DC output. And then AC DC converter, full bridge. Oh, okay. Switching AC/DC. Comprising the switching power semiconductors, the transformer, and the driver IC. Together they create a high alternating voltage for the transformer. The turns ratio of the transformer permits a step up or step down voltage as well as. I need a better block diagram here because it feels like I feel like within this you have the MOSFET, the capacitor, and the transformer. But and then you get, you know, the let me search AC/DC block diagram. If there's a better one, maybe this one. So low frequency, high voltage AC input. Here's a rectifier first, then it's filtered. So here we have the pulse DC after the rectifier, then you have high voltage filter DC. And here's the switching element with the PWM control circuit. And it goes to step down flyback transformer. So here's a high frequency, high voltage AC, low voltage AC. Does it really go through? So this is the one we're gonna make actually. Isolated SMPS flyback converter. Simplest and most common used for low to medium power applications. Quite fitting since I'm mostly using or working with low power applications. Flyback converter. Okay. Okay. More shapes. Pulse. Nope. DC. Okay, but it's basically basically we have the PWM driver and the switching element. So you get a, okay, wait. PWM driver to the switch, and then a transformer. Yeah, I'm running out of colors. But this part is basically the same in a way. So you have oh, what the hell? Oh. Okay. Basically lost it a little bit. Like, let's take it from the beginning again. So we're gonna plug this thing into the wall, basically. So we have AC power coming in to an input filter. Filters out noise in both directions. So you have common mode noise and differential mode noise coming in from the power supply. So you have maybe a choke, some filters, and then you also have something in order to filter out noise coming back out to the mains, the socket. So here then you have a filtered AC. So basically it's a cleaner signal. Then it goes through a rectification part or stage where it strips away the negative portion. And then you have more a pulsed DC, because it's not alternating anymore. Basically you strip away the alternating portion, or no, the negative portion. That's easier to understand. And then you go through a active power correction phase. I mean, either active or passive. You can use passive elements in order to have a more of an in-phased pulse DC, meaning that input current is in phase with the input voltage. Here then you have the pulse DC. You have the DC signal, which is switched on and off via a PWM driver. So you can essentially set a higher frequency output, right? So here, this I need to draw up, I think. So basically here, so something like this, and then something like this. I was doing so good. So basically, yeah, you can definitely see the difference. So high frequency, lower frequency. Wait a second, right. Low frequency. high frequency. But is this AC then? I don't get that. Why would it be AC after? In a SMP or AC/DC SMPS, after the switching element is the AC voltage, AC or DC. It's a square wave pulse. This pulse DC is then sent through a transformer to adjust the voltage level and then through another rectifier filter to produce a stable DC output. Okay. So it goes through the transformer. Here it has so here we have the isolation, right? And then through a rectifier again. And the filter. It's still, but it's still an in-phased pulse DC though. Phase pulse DC. So and then here we have the end product. Stable DC outputs. But, or we're not finished yet. I just wanna, I'll do a bit like this, this. Kind of like that. Then you have it filtered. Rectification. Low frequency pulse. And then high frequency square wave, because it's the switching output. Here is the isolation barrier, you can call it. Where, and here is the actual step down action. Step down. Stepped down voltage or DC. And filtered, we know. But going back to this, so after a rectifier, you have a secondary ground, your primary ground, so on this side of the transformer, and then on the secondary ground on that side of the transformer. Then it goes through a reference error amplifier to an optocoupler. This is probably in the driver IC itself, maybe this part. It just takes in the DC out. Passes through a rectifier to the load. Smoothing capacitors and filter components also form part of this function. The output voltage also feeds a comparator amplifier, which compares the output against the reference voltage to provide tight voltage regulation. For feedback to the primary PWM drive circuit, adjusting the drive accordingly to correct any output voltage deviations. Yeah, but that's it, basically. Yeah. I will draw it up, even though it's basic. Damn, I say basically a lot. Up to compare. Error reference, or what was it? Error. Reference error amplifier. Reference amplifier. So this part, this yellow part, I'm not sure if this is working together, like if it's a chip or something like that. But it basically takes the output and feeds it back in order to have the correct regulation, I guess. So if there's any errors, it compensates. So if you have like a short circuit or something, where it's, or yeah, a short circuit that all of a sudden draws a lot of current, something like that, and it has to compensate. I don't know. Or heavy load or something. It takes that in and it adjusts accordingly. But the second rectification stage, smoothing capacitors and filtering components also perform part of this function. Double voltage also feeds a comparator amplifier, which compares the output against the reference voltage to provide tight voltage regulation. Now, but yeah, so here you have the input. So we're still on very high AC and then DC voltage, so 240. And through this transformer, based on the windings, you have a lower voltage, a step down voltage, which goes through rectification and input filter, output filter. filter. Why not? And then you take that stable DC output, measure it, compare it to a reference, like an error reference or something like that, and then send it through a optocoupler, which is also isolating the secondary part of this transformer to the primary part. So this side is grounded here, this side is grounded here. And then you adjust accordingly. That's the operation, and that's what we're building. That's what we're building. Cool. Da, 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 da. So where do we start with that? Where do we start? We need to design or basically set up the characteristics, like the requirements for this design. Like we have a 240 voltage input. How much voltage in socket? Sweden. 230. 230 volts at a frequency of 50 hertz. Okay, so 230. Okay. So we have 230 volts input. And then what type of output do we want? 12 volts. Maybe. Yeah, let's build a 230 volts, or I guess we're not building that, but we're just taking an example from Sweden, right? What we have in the socket here, which is 230, but it can be from anywhere between 90 and 265 volt AC and 50-60 hertz. I think we use 50 hertz. In the US, maybe they use 60. And then we need to create a filter for that. Fuse, surge protector, EMI filter, chokes, capacitors, rectifier. So basically, after the rectifier, it's still not a clean DC, right? I guess that's what we get from this part. Okay. But we touched upon it before, if I remember which one we want to build. Where was that? Where did I Google that? Flyback converter. Flyback converter. Flyback. Okay, maybe it wasn't that one. Fly. There are several topologies in use for AC/DC power supplies that provide isolation and highly energy efficient in operation, the most popular being the flyback and quasi-resonant method. AC/DC flyback converter. Wait. Okay, let's do a quasi-resonant flyback then. How quasi-resonant flyback works. Detailed operation. So variant of flyback converter wherein it makes use of the parasitic elements to partially resemble a resonance action. According to dictionary, the word quasi could mean... What page is this? Design guide for QR flyback converter by Infineon. This could be good. This is perfect. The quasi-resonant flyback is simply a DCM flyback having a valley switching turn on. It is also known as variable frequency or valley switching flyback and is largely used in low-power SMPS application such as charger, adapter, and auxiliary supply. The objective of this paper is to develop a practical step-by-step and easy-to-follow approach in designing an offline QR flyback power supply. This includes quick component selection guide, design knowledge, and practical tips for a fast and optimized design. So here we have the bulk capacitor, the transformer, the switching element, and EDS. Oh, drain to source. So how much is here, basically. And the V out, which you can't see here. Figure A shows the basic flyback converter schematic showing the primary parasitic components, L leak and CD. Leakage inductance of the transformer, while CD is the total capacitance, C OS plus intra-winding capacitance, stray capacitance of the drain node. We shows the normal VD's waveform of a DCM flyback. I need to read this more. And okay. I would just write this down here. So let's make a QR flyback. So this is a quasi-resonance flyback converter. Wait, okay. Figure 1A shows the basic flyback converter schematic, showing the primary parasitic components, L leak, and the CD. L leak is the leakage inductance of the transformer. It's here, I guess, and CD. Okay. And CD is the total capacitance, C OS plus intra-winding capacitance plus stray capacitance of the from drain node. Figure 1B shows the normal VDS waveform of a DCM flyback, where two resonant oscillations can be observed. Oscillation 1, oscillation 2. A higher frequency oscillation 1 happened during the initial turn-off of the MOSFET due to the leakage inductance resonating with CD. Okay, so the leakage here resonates with this. Oscillation 2 happens when the secondary winding, this part of the transformer, energy declines to 0. During this time, both windings are open, thus LP resonates with the capacitance at the CD node. Because of this resonance, VDS will experience a minimum valley point, whose minimum value will depend on flyback reflected voltage, VR. By making the controller to turn on at this minimum value, we then have what is called QR, or valley switching flyback, whose minimum value will depend on flyback reflected voltage. So you basically have it. You have this resonance between L leak and CD, and does LP resonance with the capacitance at CD. So it resonates between each other at different points, and VDS will then experience a minimum value point, whose minimum value will depend on flyback reflected voltage, VR. I don't see VR here, but by making the controller to turn on at this minimum value, we then have what is called QR, or valley switching flyback. Ooh, this is heavy. Depending on the QR controller, the MOSFET can be turned on at different valley the drain source voltage, first, second, even 7th, depending on the loads. If it is always turned on at the first valley point, it is called free running quasi-resonant mode. The free running QR, the frequency is adjusted depending on the load. Figure 2 shows the frequency versus load relationship. So the lower the frequency, the higher load. The frequency is minimum at maximum load while increasing at lighter loads. No. Okay. Okay. So this is efficiency. It's an efficiency thing. So you have this resonance from L leak. What did it say exactly? The higher frequency oscillation 1 happened during the initial turn-off of the MOSFET due to the leakage inductance resonating with CD. So it's when it turns off, there's leakage inductance from the transformer that will resonate with the capacitance from the MOSFET, which is some stray capacitance and some other things. That's this one. And then when all the energy from the secondary transformer is 0, it declines. Secondary winding energy declines to 0. Both inductors, both windings are open. Okay, but both sides or both windings are open. And the LP will resonate with the CD. That's the secondary oscillation. And because of these resonances, the VDS will have valley points, which is minimum valley, minimum points. Okay, so then if the MOSFET then is turning on when these, right at when these things happen, these valley points, these minimum valley points, there will be less switching losses. Why exactly? Okay, yeah. So you have switching losses if you turn the MOSFET on while the MOSFETs still have energy across it. So if you wait for this minimum value point, the MOSFET is completely off. You don't have this, or you have less at least. The secondary winding energy declines to 0. During this time, both windings are open. Thus, LP resonates with the capacitance at the CD. And that is why, or where the term comes from, this valley switching. Valley switching. So you turn it on, you turn the MOSFET on at this minimum points where there's no energy across the MOSFET. So you have less switching losses. Okay. Okay. Which is also called quasi-resonant. Okay. quasi-resonant flyback converter. So it's an efficiency topic. Okay. QR flyback design equations and sequential decision requirements. This is old. 2013. Okay, this is very heavy on some calculations. Let's do a little bit more research. Here maybe it could be something. This is basically component. Design guide for quasi-resonant flyback topology. So design guide for quasi-resonant flyback converter using Infineon's latest coolset 5th generation QR Plus controller, which offer high efficiency, low standby power with selectable entry and exit standby power options. Okay, we need to Here you have the another transformers outside of its optocoupler. So I guess this is just a controller. Yeah, but I guess we need to start with the controller, which could be this one. I'm gonna search converter IC or controller. Controller IC. Schematic, PCB design. This one we could do, in all honesty, since it's 49 pages. SDM also have a, that could also work though. Here's another one. Cool. So this is the L6565. So this have VCC, so the power input, ground, GDCS, VF comp. Not familiar with this since it's is a current mode primary controller IC specifically designed to build offline quasi-resonant set VS 0 voltage switching at switch turn on flyback converters. It's achieved by means of a transformer demagnetization magnetization sensing input that triggers MOSFET's turn on. Going back to the basic understanding of this valley points where you have the turn-ons, 0 voltage switching, at switch turn on. Where the energy or the magnetic field of the secondary winding goes to 0, collapses. So I'm guessing you then have a demagnetization sensing input that triggers MOSFET's turn on. So when it sends a trigger, that turns the MOSFET on. So what? Damn, the camera's really not working that good, huh? Okay, but that's first episode. And I need to go.